we'll see some interesting features about how to perform micromachining on large 3D pieces, and we will learn also from the expertise of our speakers about optimum parameters to get the desired result. We will have time for questions at the end of each presentation, so I encourage you to raise your hands so you can solve the doubts directly with the speakers and we can have a rich discussion. We are also live streaming on YouTube in case you want to follow in that platform. And let me first say a few words about EPIC, in case some of you doesn't know us. EPIC is the European Photonics Industry Consortium. We are the world leader industry association in the field of photonics. And now we are 800 members. You can see an impressive number. The goal of EPIC is to support the development and the competitiveness of the photonics industry and its members. And I'm showing in this slide the great EPIC team, which allows us to be active in very different areas. All our activities are related with connecting people with the idea of generate new collaborations, to create new business opportunities, and also to learn about new markets and applications. So we organize technical meetings online and in person. We also provide market analysis and reports. We help to find the right investor for each company, or help also big companies to invest in the markets of interest. And we also support human resources activities with the Jobs in Photonics website. As an example of future activities, you can see a list of our next meetings, both online and in person. I want to highlight some of them, like in September, 26 September, an OTM on photonics for aesthetics and cosmetics. Also October 17th, the photonics for the mobility of the future, with a lot of laser applications here, also related with batteries, mainly laser welding. I would also like to highlight the EPIC Tech Watch on laser and photonics applications at COMPAMED for those of you interested in the medical market. That will be celebrated in Düsseldorf during the Medical COMPAMED exhibition. And for example, in January 2023, we have an OTM on laser-based manufacturing for implants, and also do not forget that we have the World Photonics-Technology Summit in San Francisco. But please check our website, because we have more events there with all the information. You can see the agenda, and all the topics will be really well explained there. For today, we have 6 very great sponsors. We will start with Asphericon. We have Sebastian. Perhaps you can say a few words about your company.
Yes, of course, Antonio. Thanks for having me. So Asphericon, a company based in Jena, Germany. Roughly 200 people are around. We are a manufacturer of aspheric and freeform lenses, and also systems such as beam shapers, beam expanders, for a variety of applications such as laser material processing, laser welding, laser cutting, stuff like that.
Thank you, Sebastian. Our next sponsor is LaserPoint. We also have Daniele. We will see some of your work later, but perhaps you can say a few words about your company now.
Yes, sure. Thanks, Antonio. LaserPoint is an Italian company. We are manufacturing laser power and energy meters. We have a wide portfolio of more than 100 different kinds of sensors. And we have actually also a dedicated line, which we call Blink high speed, which is specifically dedicated to measure ultra-fast laser that I think can be of interest for laser micromachining. Thanks.
Thank you very much, Daniele. I haven't seen anybody from Workshop of Photonics. This is a company dedicated to find the most effective femtosecond laser micromachining solution for the different tasks the user can have, and also to help with the process of the end user. Our next sponsor is LUXINAR. We also have Joanna in the room. You can perhaps say a few words, Joanna. Thank you.
Thank you, Antonio. Yes, LUXINAR designs and manufactures sealed CO2 laser systems up to 1,000 watts, along with a new range of femtosecond laser sources called the LXR series. These feature pulse on demand and burst mode, among other things. Our lasers are used in lots of industries, including automotive, electronics, packaging and textiles, and for many different processes such as cutting, ablation, drilling.
Also, we lost your audio. We lost your audio for a while, Joanna.
Sorry about that.
No problem. But I think that the message is clear, so thank you for the introduction. Our next sponsor is axetris. I saw music over there. Perhaps you can say also a few words about your company.
Thank you, Antonio. Yes, axetris is a leading manufacturer of micro-optics, including micro-lenses, and also micro-lens arrays and diffractive optical elements. So our micro-optics is famous for telecommunication transceivers, but also our micro-optics and diffractive optical elements beam shapers can help in laser machining society. So I'm here today for that, and I want to hear your need of micro-optics or beam shaping components. Thank you.
Thank you, Music. And our last sponsor is DMC. DMC is a company making software for laser machining system control. I saw Tauras in the room. Perhaps you can say a few words, Tauras.
Yes, thank you, Antonio. Yeah, DMC, we're a Lithuania-based company. Our solution is used to control laser system machines for any kind of application, from laser micromachining to 3D printing. It's used by OEMs, end users, R&D institutes, and we're one of the biggest for laser system control software providers. Thank you.
Thank you very much. In this slide, you also have my contact, the contact of my colleague Antonio Raspa, who is helping me with the moderation today. Any question that you have in mind, or you perhaps realize after the meeting, you can just contact us, or if you have anything to discuss, feel free to contact us. We will be really happy to help. So, Antonio, I think you are going to tell us a little bit about the audience we have today, and all the supply chain related with micromachining.
Yes, sure. It's really an interesting restart after the summer break. Here, I'm really impressed because in this slide, we have all the people attending the meeting of today. And what is really catching my attention is the end user box, where we see how relevant are micromachining for so many different industries. We are going from healthcare to semiconductor, from high performance material to lining and luxury goods and jewelry, without forgetting oil and gas, glass-based manufacturing, and so on. This really is starting an interesting revolution in the laser material processing. So I just would like to remind that if somebody has not his logo in this slide, it's just because this slide is showing the people that are in the room today. Clearly, there are many other potential users and company involved in the supply chain. This could be really to invite them to join our future meetings. And then let's start with the speakers. We have a very interesting panel. Can you go to the next slide, Antonio?
Yeah, I'm sorry, Antonio. I'm freezing right now.
Because I don't remember all the names.
Let me try to share again.
Okay. But while Antonio is looking for the slide of the panel, I would like just to remind three important initiatives from the European Commission. The first one is PhotonHub, that is a digital hub, digital innovation hub that is supporting all the photonics application with a special target to the not photonics end users. And this is really a great opportunity to expand our technologies outside the standard limits. Then there are other two interesting initiatives. One is LAMPAS. LAMPAS is a project that is oriented to laser manufacturing of large surfaces and structuring of large surfaces. And the second interesting initiative is Pulsate, that is promoting laser-based advanced and additive manufacturing technologies in industry sector. Okay, let's go to the panel of today. Today we have Andreas Gaab from Corning Incorporated. Then we will have Tim Kunze from Fusion Bionic, Rainer Kling from ALPhANOV, Dariusz Świerad from Fluence, and last but not least, Francisco Gontad from AIMEN. So I will go straight to Andreas. So let's start talking laser. Andreas, the floor is yours.
Good morning. Good morning or good afternoon and good evening all around the world. So let's start sharing the content. Okay, can you see my screen now?
Yeah, we see the screen, Andreas.
Okay, great. So yeah, thank you. First of all, thanks for the opportunity to present what Corning is doing with lasers and glass. And I'm currently located at the Corning research facility in Corning, New York, US. So you see the site in the background here. So we are here, a group of some 1,000 scientists and researchers working on processes and development that can lead into future products, mainly based on glass, ceramics, and things Corning is doing. I personally, I'm working on the laser processing side here at Southern Park, and I did work the past 5 years with Corning laser processing in Germany. So that's also why this talk is also focusing on glass cutting mainly. First, I like to give a quick introduction into Corning and why Corning is working with lasers and laser manufacturing and laser processing. Maybe you know Corning is a quite old, long-standing US company focusing on glass and ceramic materials. We do have currently more than roughly 60,000 employees worldwide. So we increased that number on that slide continuously. And we are trying to develop products and processes that help to transform industries and also Corning people's life. So one of the most famous products Corning provides is probably the Gorilla Glass, you know, or from these smartphones. But the product portfolio goes well beyond that, mainly based on glass products and glass ceramics. And why is Corning also working with glass? This is mainly because Corning is interested in a lot of industry shaping innovations. So from its beginning, Corning tried to really find new products that can be used all for interesting applications, starting with light bulbs for railroad signal lenses, but also spreading through kitchenware and other technologies that might not sound like high tech, but the products and the manufacturing processes were always new and innovative. And as you see here on this track record, in 2013, it's given that Corning focuses also on laser processing of glass, mainly to support the development of the glass cutting process that has evolved during that time with the emergence of the short pulse picosecond lasers. And since that time, Corning has a site that focuses on glass cutting, is providing tools and solutions for that, but also uses it internally for manufacturing and production. Corning is very strong, very proud of innovation, and for sure also on intellectual property. So that's what's also driving that site here in Southern Park, where we do try to innovate and bring new solutions to products. And to this intellectual property also belongs the so-called bezel beam technology for glass cutting. You might have heard of that, which is a way to very specifically focus the short pulse laser into the glass surface, into the glass bulk material in order to enable later on separations. In case you like to understand more detail of this, you're welcome to reach out to CLT or to me to explain some details on that. So this is a site where Corning focuses on manufacturing for the semiconductor industry, but also 2 sites where the laser processing is pushed forward. As discussed, this is on the one hand side, this Kling site close to Munich in Germany, so-called Corning Laser Technologies, and they do provide full automated laser processing solutions for glass cutting, but also for glass processing. And the other site is where I'm currently located, the Southern Park site in Corning, New York. That is a small, nice town, upstate New York, close to Rochester, where we do apply this technology for internal investigations. So what can we do with this technology? Why do we think this is a great technology? So first of all, one key process we can realize with that and with the tools Corning can provide is we can cut large, thin glass sheets, which is also one of the key core competency of Corning. I don't know if you heard that, but Corning can manufacture Gen 10 large glass sheets, which is 5 by 4 meter large glass sheets with a thickness of below 1 millimeter. So with a very high aspect ratio of that material. And this we can directly laser cut into shape with this, based on this technology. Another application on a very different scale is really more in the area of micromachining, where we can cut freeform shapes directly from finished processed glass wafers. One application here is, for example, the augmented reality, where you can cut then gratings and waveguides from imprinted or post-processed glass wafers to enable the augmented reality industry. Another application for that, which is also initiated and established at CLT, is that we can directly cut 3D formed glasses. So not only flat sheet of glasses, but also if you have hot formed or bent glass shapes that need to be trimmed into exact shapes for your product, you can then directly cut these 3D formed glasses without any movement of the part or any robotic assistance. One other technology that had been emerged during the research and application development at Corning is that we were able to increase also the quality of the cutting. So the blue dots you see here, this is a typical performance for edge strength. So if you have a laser cut edge and you bend that, at some point this glass will break, and you can measure the stress that is required or that is the limiting factor until this break occurs. And with enhancement of this laser technology, we are able to shift this edge performance of glasses really by a factor of 2 to 120 megapascal in 4-point bending. So when you have heard from other publications of people that glass is weak and after cutting glass always breaks and you do need post-processing, with modern development in this field, we are really able to bring this cutting performance to the next level. So last but not least, here's one detail of a laser cut edge. So this is a 0.7 thick glass sidewall, and we can control the laser beam in a way that we not only modify the full glass thickness of the substrate to enable separation, but we are also able to control the depth of modification inside the glass in a way that we can leave end facets on the glass side that are clear, so that then can enable in-coupling and out-coupling light. For example, here as shown for ion exchange waveguides on the surface of the glass wafer, but this can also be used, for example, for other glass waveguides in the glass, and can enable future applications for telecommunication applications. And last but not least, I have one more example, which is very new and very interesting. besides cutting these thin sheet materials from Corning, this technology with the new powerful laser systems that are available today, we also are able to make a single pass cutting of really thick glass materials, given in this example here, up to 7 millimeter. And this can be realized even for free-form shapes as given here as round shapes or round corner rectangles. And this is true not only for soda lime, but also for different glass materials, and can be applied for many different kinds of applications. And one detail I also would like to focus, because this is a new offering that Corning has established in the last year, and which also will be promoted in the Glass Tech conference in 2 weeks' time in Düsseldorf. This is that we also can now process really small parts from a wafer-based. So if you do have a wafer process on glass where you do have a surface structuring and you need to singulate dies at the end from this wafer, you can use the laser process to modify the glass. But given that you have very small dies typically in many of these applications, you need also then a way to separate that. And we are able to now provide the full solution from lasering and breaking these dies into singular dies for example, flow cell applications, but also optical applications where you would like to have filters or cover parts for MEMS devices. And here on the top right-hand side, you do see a video that is you can find on YouTube, where you do see some nice sketches of this process. This is all I wanted to show today. If you have any questions on glass cutting or laser processing for glass, please reach out to Corning Laser Technologies in Germany, or also our Corning site, or me directly personally. And if there are any questions, please go ahead. I'm looking forward for interesting discussions.
Thank you very much, Andreas. Really nice. What is Corning, a reference in glass material, doing nowadays in terms of laser micromachining? So it's time for questions. As I mentioned, we'll appreciate if you can raise your hands and ask your question directly to Andreas.
I have a question.
Yeah, Dariusz,
Andreas,
please.
if you don't mind. Thank you very much, Andreas. It was a very fantastic talk. And I have a question regarding the 7 millimeter glass cutting. So what is the speed you can obtain?
So given you have the right laser source in your system, given you have the right laser source in the system, you can do that with a single pass cutting. And given that the picosecond lasers do have a very high repetition rate, you're typically not limited by the laser performance. You're then typically limited more by the dynamics of the axis. So I think I would not pretend that you can go with 1 meter per second on any given structure you have, but you are in the realm of hundreds of millimeters per second for sure for this process, if given the single pass approach and the right system selection.
Okay, thank you. Very impressive.
Yeah, thank you.
Yeah, another question from Ali from CMS. Please, Ali.
Hey, how are you? I have a quick question, please. When you do the process for the glass cut, would you prefer to use a scan head, or you use a hose with some air pressure or something like that?
The process for glass cutting is not based on a scan head application, but it's processed on a fixed optics application. So you do have to translate the laser beam with a fixed optics. But given typically tool building capabilities, this can be done very quickly. Did that answer your question, or did I misunderstood that?
Yeah.
Yeah, right. So this process we are utilizing is not an ablative process. So typically, when you do think of cutting of glass, you probably would go with an ablation with a green laser source or so. But this is very slow. So our process is really based on a single pulse, single pass, laser cutting at high speed. So you can achieve these 1 meter per second processing speeds on straight lines on large sheets.
Yeah, because I'm doing several projects in glass cutting with different types of lasers between pico UV to IR. Thank you so much.
Yeah, so one big advantage, as you just mentioned, that is that we do not create debris with our process. So if you have an UV ablation process, you always create some ablation. Your sidewalls are never straight, and you probably also get quite some heat affected zone on the surfaces or inside the material. Given the Corning technology, we use picoseconds lasers, which are quite cool for processing these materials, so we don't have too much heat affected zone, and the process is clean, so we don't create debris or dust particles.
Thank you.
Welcome.
And another question, my colleague Antonio, please, Antonio.
Yes, thank you so much, Andreas, for the great presentation. I saw that you gave example from very large to quite small devices. So
Yes.
I figure out that also the laser, you are using different laser and different processes.
Right.
If you can tell something, and also maybe if you can tell us what is still missing. So I think that you have in your hands a lot of laser, but it's enough, or there is still something that you need?
So this is a great question. Thank you for that. So the high power lasers are for sure very important for the thick glass cutting. And there is still need to really integrate and have these available at a good cost point, because these are not yet too widely spread. And if you do not have the laser power you do need to have multi-pass cutting, or you do need to live with a very narrow process window. So powerful lasers with a very good beam quality and a tunable pulse duration, not pulse duration, but pulse profiles. These are required to really optimize these processes to a good matter. On the other side, what is really required is to optimize the component selection and the integration of the part to the customer expectations. So what we do typically need is to understand the customer requirements in a very great detail, because what sometimes happens is that the customer has a problem on a glass part, and he is used to classical manufacturing like score and break, cutting, grinding, and all these things. And typically you can't directly laser process these parts because of blocking features, because of other structures that are there. So it's really important to discuss at an early stage with the end customer what enables and disables laser cutting. And then we are able to also establish a process that is stable and meets the customer requirements.
Good. So I can summarize that you are really following or mentoring the customer on laser application. Right. Because it's like always.
Right. So if you approach Corning Laser Technologies, they will not provide you with a solution and you can go with that and just build up the tool. You will need to discuss in greater detail how the tool will be set up and designed, and we will define the process so that it matches to your application. So this is what we typically do. Good.
Thank you so much.
You're welcome.
Thank you, Andreas, and thank you, Antonio. We also know a little bit more about the needs of Corning for the future, so it's great to have this information. So I don't see any other question in the room. So thank you again, Andreas, for the nice presentation. It's time now for Team Kunze from Fusion Bionic. We are going to learn a little bit more about surface structures and DLIP process. So, Tim, the floor is yours.
So, hello. I hope you can hear me. Can you see me? Can you see my screen?
Yeah, we see now the presentation on, and we hear you. Thank you.
Okay, perfect. So, first of all, congratulations, Epic, for having 800 or more than 800 members. That's a great progress. And hello, everybody. So, my name is Tim Kunze, CEO of Fusion Bionic. We are a spin-off from Fraunhofer Gesellschaft, Fraunhofer IWS in Dresden, Germany. focusing on laser surface finishing through an advanced laser technology called direct laser interference patterning. And I would like to bring to your attention today a little bit the world of bio-inspired glass surfaces. So it follows the talk of Andreas using laser surface finishing. First of all, of course, it's what bio-inspiration means. Biomimetics is a synonym for that. So first of all, of course, you can take some inspiration from natural surfaces like the lotus leaf effect or lotus leaf and the moose eye, and then look at a smaller scale and then observe some nice textures and features, and then transfer that to technical surfaces. So this is, let's say, the short version of what we do. So from nature to innovation, so we are aiming at transferring natural effects to technical surfaces on different levels and for different kinds of applications. And how this looks like in reality, so to say, or just to give you some example, is shown here. So this is an example of the lotus leaf surface, which consists of different kinds of structures, different kinds of, let's say, chemical, let's say, compositions, which you don't see, of course. But the idea is, of course, to mimic that, to produce that artificially by lasers, like shown here. So this is an example of our approach. Of course, it looks more, how to say, more ordered in the sense, which does not necessarily mean it's better in the end. But this is one of our core approach, let's say, to transfer these kinds of effects from nature to technical surfaces. We therefore provide certain kind of solutions, technical solutions, which are capable of doing that. In this case, it's a demonstration of our core modules, so one of our products. And the technology behind that is based on interference principles, meaning that we use direct laser interference patterning, which we developed over many years at the Fraunhofer IWS, and as a spin-off from the Fraunhofer, we now bring this to the market. And basically what is different from established technologies is that you work with interference principles, meaning that you, from, let's say, originating from a laser source, you take the laser beam and then control the kind of number of laser beams, and also the way how the laser beams are overlapping, and this can generate some surface features on the product, on the material. So actually, we overlap laser beams, which result in interference pattern fabrication, and this in the end can be used to treat materials. So actually, what we have in the beam is some sort of a structured beam, which is then imprinted on the material. What we now do at Fusion is to realize technical implementations, meaning that we have different kinds of products which are based on interference principles, based on the interference technology, and then provide this to the market. Basically, this kind of technology can be used on all kinds of materials at very high process speeds, because you usually are not, how to say, it's not mandatory that you need to, or actually you don't need to work in the focus, which makes it highly scalable, especially if you have more and more power available from the laser sources itself. Recently, for instance, we demonstrated at the end of last year that you can reach a processing speed as high as 3 square meters per minute, which makes it very interesting for various applications. I today want to focus, as said, a little bit more on the glass material applications. So, for instance, for consumer electronics, and here photovoltaics in the first place. With consumer, for instance, there's a lot of challenges, especially when it comes to optical properties. And the second, for photovoltaics, for instance, contamination is very important. It's something which occurs and which needs to be controlled on the long run. Just to give an example, this is, for instance, an anti-glare functionality realized with laser, actually. And one need to know, actually, that anti-glare is basically the way how a reflection is controlled on the surface itself. So it's some sort of scattering process, which is of course different than a real anti-reflection, let's say, functionality like shown before from the mood eye. And what we can do actually is we can provide, let's say, an approach and an alternative to chemical etching. So this chemical etching is, for instance, a process which is very common. It's, I think, more than 250 years use in this kind of for laser for glass processing, and you can reach comparable results on using lasers, which of course makes it very interesting from a sustainability point of view. And of course, you can be much more flexible and can, let's say, of course, on the long term also be competitive even for large areas. A second example when it comes to the second field, so photovoltaics, is anti-soiling. It's some sort of, I would say, newer functionalities, meaning so soiling in general is a challenge for photovoltaics because you can imagine that the photovoltaic panels, which are out there in all kinds of environments, are usually prone to different kinds of soiling phenomena like mineral dust, dirt droppings, algae, and so on. And this is not a small problem. It's, of course, it can scale up very quickly. So in the range of 7% of solar power production is lost due to this kind of contamination, which can easily sum up in the billions. And of course, usually you address that by cleaning, which consumes a lot of water. Anti-soiling coatings is a different way, but there are different kinds of solutions out there. And we, from Fusion Bionic, are offering a different kind of approach, obviously by laser texturing, aiming at large area treatments to actually address also the adhesion of particles in the end and provide a more self-cleaning or better self-cleaning mechanism. If you go for other kinds of examples like aesthetics and, for instance, also sensor applications, then of course laser processing can also provide some alternative and some solution here. Obviously, for aesthetics, if you want to go for colored glass, then usually you use additives, which can be a problem, but of course not in all areas. And for sensors, the problem is different. It's with fogging, for instance. So you know that, for instance, from goggles, if you come in from outside when it's cold, and then you have this fogging effect, which is definitely annoying. Decoration, of course, can be addressed by surface structuring also, of course, which introduces some diffraction, effect. So it's some sort of, let's say, color effect, which is depending on the angle of view, but it can introduce some aesthetical nature and some interesting decoration effects, which are, for instance, relevant for the consumer and beauty industry. And the second example, which I've brought you with me, is anti-fogging functionality, which is, for instance, usually done by polymeric coatings, for instance. So a coating approach, and we can also provide an alternative here. Obviously, also much more flexible than a coating, so we can really work with logos and stuff like that. And actually, what we are aiming at is really to find new and provide new ways to substitute established processes like mentioned coatings, chemical etching, and so on. In the spirit of the EPIC, of course, I would like to highlight two things: so what we can do for you and what you can do for us. So on the left-hand side, so what we can do for you is, of course, that we see us as a solution provider making new functionalities or advanced functionalities available, like shown. But of course, there are others. And I just showed today more the glass field, but of course, there are much more materials where we have experience, so it's not limited to glass. In this spirit, we, for instance, provide customization of surfaces, meaning that we can help you in advancing your products, but also in the same place, let's say, provide the manufacturing solutions to achieve that and bring this to your production line. On the other side, of course, what you can do for us is that we are constantly looking for customers interested in alternatives to established solutions, as mentioned before. And this, of course, can involve also some joint activities, joint projects in, for instance, working together on surface functionalities at advanced one, or of course at upscaling or on upscaling scenarios, which means that, of course, at a certain place to really upscale, for instance, direct laser writing processes when it comes to high resolution features. And with that, I would like to end my presentation. And I would like also to highlight that we are also participating as Andreas and as Koning at the GlassTech, and would be happy, if possible, to meet you there. Thanks.
Thank you very much, Tim. Really nice overview of your capabilities. So again, it's the time for questions. So Arnas from Fentica, thank you.
Yes, hello, Tim. Nice presentation. Thank you very much. I was wondering about the lifetime and the durability of the surfaces, because yes, could you comment on that?
Sure. I think maybe I should put that in the future because it's the all-time question. Of course, relevant question, important question. It's depending, of course, on the functionality, on the area, the functions are applied. Just to give you an example, this anti-fogging surface, which I've shown you, is more than 1 year old. Also cleaned continuously, though it is. Of course, if you take a sandpaper and then rub on it, then of course, I mean, of course, if a functionality is there or not, it would definitely destroy the surface. But it depends on many things, and of course, one needs to talk about details here.
Got it. Thank you.
Thank you, Ernest and Andreas.
Yes, hi, interesting talk. Thank you so much. I just have a question on the surface features you're creating. So as far as I see, these are always regular features over a larger area, right? Can you also create randomized structures over a surface?
The question you are raising is not surprising, Andreas, a very good question. Yes, so basically, you're fully right. So interference technology is a periodic technology normally. But there are ways, let's say, to overcome that if a functionality like maybe some visual reflection or anti-glare is demanding that.
Great, thank you.
Thanks.
So thank you, Tim. Another question from Tim. So I have a question regarding one comment in your last slide, or almost the last slide. It's about the upscaling scenarios, because you have a technology with the laser, with beam delivery solutions, movement system, and so on. Do you think all those components are prepared for going to production in terms of anti-fogging solution, for example, in a big production? Or are you missing something from the technology point of view, or something that should be improved in all those parts?
Yeah. Are you referring to the function itself, or to the components which are used for the manufacturing solutions?
To the components.
Okay. Also good question. Of course, we are always using, let's say, suppliers which have commercial solutions. So we avoid fully, let's say, the use of experimental solutions and so on. But of course, we are also open to that. So short answer is we use commercially available. We choose commercially available solutions, optics, and so on, to be then coupled into our products and solutions as well.
Mm-hmm.
Does it answer the question?
Yeah. Okay, thank you. I have another question from Kylabs, Gwen, probably regarding beam shaping.
Hi, buddy. I don't know if I should put my camera on, maybe.
Hey, Gwen.
Hi, Tim. Very nice talk.
Hi.
I was just wondering, I think you didn't say it, maybe I missed it, but how many beams, what's the range of the number of beams you are making interference with? I guess the minimum probably is 2. Maybe not, maybe it's 3, I don't know. And
no,
maybe it's confidential, I don't know.
Also a good question. Then normally, I think what is very established, so to say, so if one can say that for a young technology like this, 2 to 4 beams, let's say, of course, you can go also up to 6 beams. Usually, there's no big difference in going higher than 4 beams. But of course, some applications might require that. And let's say from the solution point of view, of course, there's we have certain products which are a standard, so to say, so standard product portfolio which are operating between 2 and 4 beams. But higher beams could be also interesting as well for if you want, for instance, want to control polarization or things like that.
Okay, thank you.
You're welcome.
So if there is no more questions for Tim, I want to thank again for a nice presentation.
Thank you.
And I would like to introduce our next speaker. It's Rainer Kling from ALPhANOV. We continue with surface structures. So let's see what ALPhANOV is going to offer us today.
Yeah. Thank you, Antonio. Thank you all for being here and for giving me the opportunity to give a small pitch here on ALPhANOV activities. Do you see my screen? Okay, good.
That we do.
My name is Rainer Kling at ALPhANOV. We are here in Bordeaux, and today I will build up on what Tim already said, having laser texturing for functional surfaces on industrial applications. And just a few words about ALPhANOV. We have been created in the year 2007 as a non-for-profit organization. We have grown to 105 full-time employees by now. And our mission is to bring photonics innovation with laser processes into industry. So we have pretty much the same range of activities of what Tim already talked about. We are trying to address surface functionalization by texturing of surfaces and in particular addressing the nanometer scale. So the chasm is really to have the nanometer precision, but at a speed of square meters per minute. And here is an example of antibacterial surfaces where it has been shown that an antibacterial surface has to have a texture of periodicity around the size of the bacteria, so below the 1 micron scale. 200 to 500 nanometers is perfect for stressing bacteria, and so the surface can be antibacterial. Our solution is to apply high average power femtosecond lasers, but with the right system technology to address the square meter scale, to have an initial mirror polished surface textured with the necessary function on the surface. And in this example here, it's a mold for a dishwasher where we wanted to have the antibacterial surface on the plastic component molded onto plastical parts for a water tank. What do we need for that? Well, first of all, a very powerful femtosecond laser. Here we have a Tanger of more than 300 watts of average power from amplitude. And that laser source we inject into a polygon wheel, a scanner with the line of 350 millimeters of length. And with the right coil speed, we address exactly this range of square meters per minute on stainless steel coils on a roll-to-roll coil, on a roll-to-roll machine. But right now, we have two different machines. We can do the batch processing for rigid and large parts, but we also have for continuous processing the roll-to-roll machine, which you can see here. And I would like to share with you a short video on the next slide, which gives you an impression of the real speed of the texturing of the metal sheets in a continuous process. And the real challenge is the synchronization of the axis of the scanner with the laser in the megahertz range. But if everything works correctly, then you manage to make test runs on coils of 50-meter length that you can see here on the bottom of my screen. You can add the function on large coils exactly that you want. So we have built this machine within the framework of the project, which is called New Skin. So imagine that like a swimsuit, you put the new skin on whatever component you have, but not only on 2D components. The mission really is to bring it on industrial surfaces for steel construction, for water treatment. And we already had the question, if you transform your material afterwards, does it withstand any forming, any post-processing process? Well, we believe it does, but we need to look into each application separately. But what we can provide to the different materials is the different surface topographies and the physical function that Tim already addressed. It can be super hydrophobic, super hydrophilic. It can be anti-biofouling. It can be for medical applications, antibacterial. It can be self-cleaning, or for photonics components, it can be anti-reflective. And each function needs a different topography. And for that, we have now ready the machine that can provide this functionality. So that's the value proposition. Within the new skin project, we have open calls. So if you have an industrial application for such a function, you can address to us, to the project, and inject your application, and we can test whether we manage to bring the function on your specific component. But the missing link for the industrialization is really the quality control of nanometer scale surfaces in mass production. So what you really want to have is a inline measurement tool that you can integrate into your machine, and within the process, within the same machine, you already have a feedback whether your nanostructures are implemented into your sample or not. And this is a big gap. Most quality controls of nanometer scales are made offline, and you have to use microscopes, but nanometer structures you cannot see in microscopes. So you use an AFM or SEM, but this is no inline tool. So what we suggest is the scatterometry as a tool for inline process control. And I don't have the time to go into details how it works, but basically you look into the angular distribution of the scattered light, and you can conclude from that which textures you implemented into your surface. And we measured with AFM control whether it works or not. And you can see here a good correlation. If you know that you're texturing lips structures, for instance, into your metal sheet, you correlate that with a model, and then you see the height of the structures that you implemented. So the take-home message is basically that high average power femtosecond lasers are a valuable tool for high-speed processing in the square meter per minute range of nanotexturing of whatever material you want to texture. Scatterometry is a tool, a very promising tool for measuring the nanoscale structures that you cannot measure optically easily within the machine. And the next step is now to bring these functions on your real parts, on industrial parts, on 3D parts. And I don't have time here, but this will be subject of 2 different speeches. You can transform your sheet metal by forming, and we have promising results that they survive the forming process, or by replication of molding, where you texture directly the mold and then transform it to thermoplastical components, and the reproduction of these structures, even on the nanoscale, is quite promising. So with that, I would like to thank you for your attention. And here is a short overview of the different structures that can be realized with direct laser nano patterning. Thank you.
So thank you very much, Rainer. Really interesting. Also talking about the quality control proposal. Any question? Yeah, Antonio, please.
Yes, thank you so much, Rainer. Very interesting and dense presentation. I have a lot of questions. So I take only 2, but I took a lot of notes.
All right.
So, one is about the laser. So you are using now a 350 watts laser. Let's imagine to have more power. It does have any impact on the process, or we should expect now to deal maybe to some limitation, especially on the heat that we are putting on the parts. And this is one question. And then maybe later, I would like to listen something more about the anti-reflecting treatment.
All right. So the question is, the answer to the first question is, luckily, with the high-speed scanners, we are able to scale up even more the scanning speed. And we can see in the market now that polygon wheels go into the kilometer per second range, which helps you to distribute the heat over a large surface area. And with that, with the coil speed, we are not quite limited. We can have larger spots, but that will reduce the resolution, of course. But in principle, we are able to distribute even kilowatt, so 3 times the power that we are using actually, over the surface without any detrimental effects of heat effect. We believe it works. The good question is on the synchronization. We use the approach of low energy, high repetition rates. And with the high repetition rates that we are currently using, we can scale that up even further. So with the kilowatt range, we don't see the limitation. If we scale up the repetition rate, then the good question is for the synchronization going into the megahertz range. And here we see limitations in electronics, which are not well developed. And the scanner laser communication to be synchronized with the handling system, this is a real challenge. And I'm happy that we have DMC here in the audience. They listen to our needs, and the system technology in this range is really something that needs a lot of attention to go towards higher average power.
Good, good. Okay, very interesting.
So Antonio, I keep your second question for a little bit later, and we go with.
I see that there are other friends.
Yeah. We heard about surface metrology and measurement. So I see since so far Carlos is raising the hand. So please, Carlos.
Good afternoon. Yes, as I saw that quality control was somehow a limitation, I thought that it maybe was worth to ask why. So I saw that in your laboratory you have a Leica DCM 3D, which by the way is a system designed and manufactured by Sensofar many years ago. You solved the quality control by other means, and I was wondering what are the limitations of an optical surface 3D profiler? I know that roll-to-roll applications are always challenging, mostly for image techniques. What's happening there? What do you think you would need to solve that?
Well, I would judge the TRL of such a technology quite low, because in the lab it works, but in a machine, in the real-time process, you are dealing with vibrations, you're dealing with influence of different light levels, and that really going out of the depth of focus of your coil in the point of focus, it needs some more robust technologies to make the scatterometry a mature tool for real production. But at least from the specs, it has the promise, it has the performance to deal with kilohertz acquisition rates of information that you can have a full 100% quality control of your surface. And that's why we believe that scatterometry is a promising tool.
Thank you.
Thank you, Carlos. Have another question from Tim?
I know. Awesome stuff, what you're doing at ALPhANOV. What do you think, what is necessary to actually, I know that, for instance, the laser power usually on the industrial scale is normally limited to 200 watts if it comes to USP. I mean, amplitude is, I think, a little bit far away, possibly. What do you think is necessary to drive that further, to have more power, maybe to, let's say, really see these kind of, how to say, functionalities in the market at a certain point?
I believe we are coming to the hen and egg problem. If at one day somebody says that we need a productivity of 100 meters per square a day in series production, then everyone will be ready to construct a machine, select the good laser source, and select the good optical and electronical components to address this need. But for now, we are more in a technology push situation where we are making a promise. We have this open test bed where we validate for industrial needs the different performances on air wing structures, on different applications. But this is always of big groups, the research department, where they need to present internally the results and then go push internally inside the company the application into the production. And this is a long acquisition time for them to realize these structures, because they need to go all the TRL up to 9, validate that there is no detrimental effects, micro cracks in the surface or whatever. The quality control inside big companies can be quite time consuming, and this is where we are right now. People are interested, but not ready to go into production.
Okay, cool. Let's push harder. Huh?
Yeah.
Thanks.
We can do that together, Tim. Yeah.
Yeah, sure, of course.
Okay, so we have a potential effort together for the future. We have a final question from Dariusz.
Hi, thank you very much, Rainer. It's very interesting, your talk, and it gave me also some stuff to think. What you did and well, what Tim also shown, like, got me thinking, like, are you using just Gaussian beam for this polygon scanning, or you can have some additional benefit from beam shaping and beam patterning?
For now, we are coming from the LIPS structures. There, the Gaussian beam is perfectly fine. For the DLIP, I believe that top head profiles would even have a more regular structure if it's needed. But for now, they are not used very much, because each optical component has a loss of average power, and we are trying to bring the most average power on the surface possible. So we try to minimize optical components. But on separate applications, I can believe that top head profiles are perfectly suited to the needs of industry customers.
Okay, thank you.
So thank you very much, Rainer. Really nice presentation. Antonio.
Yeah, sorry. It's correct to say that probably a challenge now is also on the components or on the optics level. When we are speaking about this industrial application, we have not to forget the lenses and the coating of the lenses.
You're perfectly right. Rudolf Weber from Institute of Stuttgart gave a presentation at ALPhANOV, and I will present this year at ALPhANOV as well, go further into the forming and whatever, saying that thermal lensing becomes to be a problem in femtosecond laser applications when you address the kilowatt range. And this is perfectly known. It's the average power of the lenses that can cause some limitations. It's not the peak power, it's the average power. And yes, you're perfectly right. We have to look into each optical component. We're used to use femtosecond laser in the single-digit power range, where optical components are perfectly fine. But now the high average power, we have to look into each optical component, whether it's suited, whether it doesn't shift with time due to thermal effects.
So this is really a real challenge for all the supply chain to have a stable and reliable process at the end, because any small drift during production is bringing the results out of control.
You go out of focus and the process is not the same anymore. You're perfectly right. Yeah.
Okay, great. I don't know if Dariusz would like to answer back, or is still the answer from before. Dariusz, you have another question, or is?
Oh, sorry, no, I didn't lower my. Sorry, okay.
Okay. By the way, I see that if there are no other questions or comments, is now the time for Dariusz from Warsaw, Poland, to speak about their point of view. So the floor is yours, Dariusz, and tell you your needs and your.
Okay, thank you very much, Antonio. Thank you for having me here. So today I would like to tell you a little bit about Fluence and what we do in our company when it comes to micromachining. just to give you overview of our company. So we are a manufacturer of femtosecond lasers, and we base our technology on all fiber designs that are designed to not degrade over time. So for example, we do not use sesam or other degradable components, and we maximize the fiber design of our all constructions, right? So for example, we have our own oscillator, which is the heart of every system we build. And based on this oscillator that, like you can see, it was tested in many difficult environments. We built bigger amplified lasers so that they are reliable with a good lifetime. So we have our headquarters and factory in Warsaw, Poland, but we also have application lab in Wrocław, where we test different kinds of applications like cutting, micro drilling, surface structuring for our customers. So this is part of our portfolio that we are offering at the moment. So of course, apart from the oscillator, we also offer amplified oscillator, which is used for 2-photon polymerization, for example, 2 watts of power and 100 nanojoules of energy. We offer this compact Jasper Flex with 30 watts of average power, 30 microjoules. And what is most interesting for this meeting is Jasper XO, which provides the most powerful solution that we have. And it is also very versatile because in one laser you have femtosecond and picosecond pulses. And here are some examples of what we've been doing in our application lab. So for example, sapphire cutting or glass cutting or welding glass to metal and different materials. So our approach is very similar to what Rainer already said he likes. So we also, having this femtosecond lasers based on fibers, we can obtain high repetition rates, so up to 20 megahertz of repetition rate. And we go up to 100 microjoules of average energy in one pulse. So we can operate in this regime where we have high number of pulses with lower energy. And I just wanted to show you today some certain tricks and trends that can be observed in micromachining world. So when you look at, for example, ablation rates for metals, you will see that there is something called optimal fluence for the metal. And the thing is that, well, this is the point when spallation mechanism works best, right? So the thing is that you don't need a lot of energy in the pulse to actually cause this spallation and be in the optimal fluence. So usually for metals, you need just a couple of microjoules or a couple of tens of microjoules to be in this regime. So when we have a laser that generates single pulses, right, you have 100 microjoules per one pulse, for example. And the thing is that this pulse energy, it is sometimes too much. So instead of being at the top of this ablation rate curve, you are somewhere far on this curve. So your ablation mechanism is not optimal. So we like being at the optimal level. So instead of, for example, using single pulse, this is what industry already does. We use burst mode, and we like to promote burst mode so that instead of having high energy in one pulse, you split the pulse into many pulses, so a burst of pulses, and each pulse in the burst would have this optimal fluence level that causes the maximum ablation rate. So we also did our own study, and we observed that there's also something like optimal intraburst separation. So this optimal intraburst separation, it's 15 nanoseconds. So this is enough time, it gives enough time for the pulse-generated plasma to decay so that the consecutive pulse can hit the metal or the surface again and ablate the material again. So there was some study done in the past by this gentleman here. And in this study, it was they looked at what's the ablation rate depending on the number of pulses in the burst. And like you can see on this graph, the intra bars interval, it was as low as like about 20 nanoseconds. And they noticed that for even number of bursts, this ablation rate per pulse was lower. And for the odd number of pulses in a burst, it was higher, right? Which indicated that for even number of bursts, this every second pulse, it's not effective because it's shielded by the plasma of the previous pulse that was applied. And for example, here you can see our results of work we did with 50 nanosecond intra-burst interval. And you can see, so this is the different ablation rates for different number of pulses. So you can see that for 1 pulse, 2 pulses, 3 pulses, and 4 pulses in a burst mode, this level of the ablation rate is roughly the same, which means that operating in this 50 nanosecond intra-burst interval, we are in the optimal level, right? So for example, if you're doing some selective layer removal of copper or just want to ablate copper very fast, this can be done most effectively with about 50 nanosecond intra-burst interval, so that the ablation rate is the highest. Another example, because we are not only limited to metals, it's also polymer cutting, or in this example, polycarbonate cutting. So we demonstrated that by just using simple ablation and galvo scanner, we were able to obtain cutting speed as high as 0.5 meter per second for this film cutting, right? So this gives good results for industrial customers who want to cut very fast with the setup simple enough, and without, this is some alternative to using like different methods like beam shaping, etc. So if you have any questions, please ask me. Thank you.
Thank you so much, Dariusz. This is really an interesting point of view, and really pointing some critical aspect of the process. I just look, there is nobody yet making a question. So I make a question. And this is also coming back to your question, your comments of half an hour ago about the beam shape. Because here we are also dealing with the separation between pulses. Also, we have to deal with the beam profile. When you have a TM00 in the central part, you have twice the energy on the waist. So somehow you are working well above the right value in the center. So
of course, using top hats is always helpful. So this is something we are certainly going to use in the future. what I wanted, my message that I wanted to convey is that sometimes going to high energies, it's not beneficial, but instead of going to like the highest possible energies, it's better to have more pulses per second, and it's better to use spatial but also temporal pulse shaping. So top hat shaping, yes, this is very much helpful. Bezel beam shaping, this is very much helpful, and using bursts, this is the future.
Yes, sure. Here we are ready to manage the fluence on the part, and you are really driving the fluence as the name of your company. By the way, I see Eric from Amplitude. So Eric, switch on the camera and make the question yourself.
You can hear me?
Yes, we don't see you, but we can hear you.
Okay. Okay. Perhaps my camera is not working. So okay, I have a question concerning the polycarbonate. You have shown the results. What is the efficiency or the specific ablation weight that optimal we can reach?
Okay. I mean, okay. So. Maybe I cannot tell the ablation rate from the top of my head, but usually, so the thickness of the material, it was in this case about 50 or 60 micrometers, and the beam diameter was about 50 micron, between 30 and 50 micron, right? So the ablation rate, it's something we haven't measured, but I can tell you that the optimal pulse duration was 250 femtoseconds, which was much better than 500 femtoseconds, which we also tested.
Okay. And a second question, perhaps, if possible, for the results you have shown concerning the optimum point for ablation with burst. You seem to say that the physical mechanism is spallation at this point. Okay. You have an experimental evidence for that, or it's from a theoretical hypothesis from first there?
This is based on the theory, right, of how the plasma is created and how what's the lifetime of the plasma. So we can analyze the results of data that's available around. And this is our conclusion that we had, hypothesis.
Okay, thank you.
Thank you. And then we have also Simon from MKS Instruments. Please.
Thank you. Thank you, Antonio. Hello, Dariusz. I have just one short question. Those experiments with more pulses with the optimal fluence, have you been doing only with 1030 nanometers or also in the other wavelength ranges?
Again, your question is if we used only 1030 nanometers for this
Indeed,
testing. Yes. So
okay.
yes, we did. We did use 1030. We also tried using other wavelengths like second harmonic, third harmonic, but still the best efficiency we obtained at 1030.
Okay, thank you.
Okay, so I have another question or another. I have a point. Here we're speaking so much about the energy. So I think it's very important to know exactly how stable is the laser. So here, and this summer, just before summer, I visited LaserPoint, where I learned about their latest product, the latest power meter. So here I see Andrea and I see Daniele. Who would like to tell us a little more about, because they have a very special power meter and energy meter.
Okay, yes, thanks,
Daniele,
Antonio. Yes, I can say a few words. Maybe I can also share my screen.
Perfect.
Okay. Can you see it? Okay. Yes, at LaserPoint, as I was mentioning before, we are a manufacturer of laser power and energy meter. And we have actually developed a very specific product dedicated to ultra-fast laser, which is very important also in today's topic for micromachining applications. And we have actually a patent on this specific product. We call it Blink High Speed. It is still based on a thermal design, so it has the advantage that it is broadband. We can measure from ultraviolet up to infrared, even CO2 laser. Actually, this is the only sensor, energy sensor, which is capable of measuring CO2 pulsed laser up to repetition rates of 1 megahertz at the moment. And up to an average power at the moment, we can just go up to 50 watts, but we are planning to go higher in the future as average power, of course. It is, as I mentioned, specifically useful when you want to measure and check the stability pulse by pulse of your laser. For example, this is an acquisition of a picosecond laser, 500 kilohertz picoseconds. And actually, the sensor itself is even faster. We have been hearing about the burst mode operation of the laser. Just to show here, just very preliminary acquisition of burst with, let's say, intra-burst repetition rate of 40 megahertz. This is a 4 pulses, and this is a 15 pulses, 200 picoseconds. So for all your application where you need to really have a tight control of your energy emission pulse by pulse. There are specific applications where the efficiency of the process is actually critical. You need to check in each individual pulse. We do have this kind of sensor, which is really unique, we believe, on the market. Thanks.
Good, very interesting. And I think that this could be really an important piece of the puzzle of the micromachining processes to know exactly what is happening. And if I'm not wrong, Daniele, it's also possible to understand if for any reason is missed one pulses in a bus.
Correct. We are developing some, let's say, additional feature related to, of course, using this sensor. Actually, we are, developing feature where we are checking missing pulses or pulses which are either above or below a certain threshold, so that the instrument can give you a feedback, an immediate feedback, if, for example, there is a pulse which is not between a certain band that, of course, the operator can set. And this, we believe, is going to help, especially on quality check, quality control, in reducing the time in quality check, because you can detect and find exactly when an event of a missing pulse or a pulse outside the specification that you set is happened, and check the specific, let's say, part that is being worked with that specific pulse.
Okay, very good, very good. So I don't see any special comments or questions.
I just have a comment for Daniele. Is regarding your meter. Is your idea that the user can also measure in the focal point or close to the focal point, or is a tool that you want to integrate with the laser head, like a control of the performance of the laser?
Actually, no. We think that our sensor can measure also the direct beam. I'm not totally sure, 100% confident on the focal point, because of course there is a damage threshold also for this sensor, but it is pretty high. As I mentioned, we can measure average power up to 50 watts. So it is possible to measure direct beam, directly the beam, and of course you can also use to measure for example, just a part using a beam splitter. For example, if you want to do some feedback mechanism inside your micromachining application, and you want to check in real time the energy of each individual pulse.
Very great.
Great.
We have another question from Giri.
Yes.
Thank you. Thank you for a nice presentation. I would like to ask about the principle of the measurement system, because it measures broadband on different wavelengths and very fast.
Yes, actually, yes. As I was mentioning, this is still based on a thermal design. So I would say that the thermal, let's say, traditional sensor physics still holds here. And as you know, thermal sensors are broadband. They can measure basically any kind of laser wavelength. But however, they are slow, typically slow. They respond in the range of seconds or more. Actually, what we are doing here, it is not, we are not measuring the heat transfer on, let's say, in the radial dimension of the sensor, but on the thickness. And we use special ceramic, special, let's say, material, very, very thin, so we can make this kind of detectors very fast. I hope I have answered your question. As I was saying, we do have a patent on this specific design, these specific products.
Yeah, thank you very much.
Thanks to you.
And we also have a question in the chat from Ali about the price of this fast sensor, but I don't know if you want to tell us right now. Perhaps it's for a further discussion with him in private mode.
I can give a rough maybe comment about this. Actually, the most expensive part on this system is not really the sensor itself, but it is more often the electronics. Actually, for this device, we have developed dedicated electronics, which is capable, it's very fast, is capable of sampling up to 500 megasamples per second. And just to give you a very, very rough number, for the sensor, we are talking in the range of 1.5, 2K euros. The electronics is about 5K euros. So as you can see, the electronics is actually more than double the cost of the sensor itself. But actually, you could, in principle, use the sensor without our electronics.
Mm-hmm.
You could plug to a standard, let's say, oscilloscope and work out your measurement from there. Of course, we do provide also a calibration certificate with our instrument when used with our, of course, electronics. So you receive a calibration certificate traceable to NIST or PTB with an accuracy of plus minus 5% on the energy measurements.
Great, Daniele, thank you. I think we covered we answered the question of our attendee. So the next speaker, thank you again, Daniele, is Francisco Gontad from AIMEN, and he's going to tell us about zero defects micromachining in large 3D pieces, and he's going to show us some of the setups they have in the AIMEN Research Center. So we see your screen. Okay. We don't hear you at this moment, Francisco.
Sorry, I was muted. One of the most famous phrases last year. Thank you for the invitation, for the opportunity to speak a little bit about things that we are doing at AIMEN right now regarding micromachining. In particular, I will speak about texturing, laser texturing. Just a brief introduction of the AIMEN. We are a non-profit research association located on the northwest of Spain. We have several areas of work. We are working on research and development. We also provide industrial services to companies, mainly on the automotive and naval sectors. We have some testing analysis facilities that are also open for those companies or for other companies in other areas. We have some training courses with regarding testing, analysis, regarding welding and some other manufacturing techniques. Our main application areas are as I said before, the naval and automotive industry, but we have close contacts with metal mechanic industry, with energy and TIC, biomedicine or textile companies. And quite recently, we have developed a strong link to aerospace companies, as we are working with them in several European projects. I will speak about the R&D that we are developing. We have 4 areas of expertise: advanced materials, robotics and control, advanced manufacturing processes, which is mainly based on laser processes, and environmental. Inside the advanced manufacturing processes, we have divided into high power processing applications we call laser microprocessing, and lesser microprocessing applications, which are micromachining. And as I said, I will speak a little bit about surface texturing. This is a particular case of micromachining where you want to apply a functionality to a certain surface. It has been mentioned in mostly all the talks this afternoon. So I will start speaking about what we see that is the challenge right now in the fabrication of 3D pieces with laser technologies. I mean, the fabrication of laser textures on 3D pieces have several problems. One of them is the throughput. We need to do it faster. We need to do it with a high accuracy because the resolution of the structure that you need to fabricate on the surface is to be very small. So this means that you have to be very aware of what you are doing in the surface in order to fabricate a large amount of things in large areas with 0 defects. So what does it mean? It means that you need to have a very good precision and positioning system that works at large speeds. You need to have very good, reliable beam guided systems, and the ones that we have observed before, the ones that Rainer introduced, for example. Online monitoring is something which is really important, but when it comes to surface texturing, it's really difficult to achieve because of the small size of the feature that we want to analyze, and because of the fast speed of the process. And another thing that is interesting for improving this process, so to reach this challenge, overcome this challenge, is the optimization of the beam shaping that you are using to reach the substrate surface. If you modulate your wavefront with the adequate shape, you can produce a much faster fabrication speed, a very nice functionality on the surface. So regarding the positioning, there are several alternatives. If you want to fabricate large pieces, you will go to robots. The only problem with robots is that they don't have the precision good enough for the fabrication of small features on top of the surface. So in this case, you will like to combine systems, including linear motion axis and rotary axis. In this way, you can change the angle that your laser is reaching the target. You need for this, you need very good reliable beam guiding systems. If you are using a robot or you are doing rotary axis, you will need probably to use laser guiding fibers. One of the problems of these systems is that sometimes they don't keep the polarization of the laser very good. So you need to improve the polarization of the maintaining of the polarization of these systems. And the other thing, as Rainer's shown before, that the use of fast galvanometric scanners helps you a lot to improve the fabrication speed through the process. Beam shaping. Beam shaping, you can do it in several ways. One of them is the way that Tim shown in his presentation. They can do interference. With interference, you can tailor the shape of the beam that is reaching the target surface. Or you could do diffractive approaches. One of them is static, the use of diffractive optical elements. You can tailor the shape of the light statically. You will have a very good. You can have a very good wavefront and use it for the texturization of the surface. Or you could use a spatial light modulator and change from time to time when you need it the shape that you are the wavefront that you are applying to the surface in order to improve the process from one place to another. One of the good things that you can get of using spatial light modulators is that you can get get rid of the periodicity that are inherent at techniques like the use of the fractal optical elements or interference. And regarding online monitoring, as I said, it's really important, but at the moment, there are several techniques that can allow you to have some indirect measurements, like, I don't know, like correlation, having a correlation between the beam characteristics, the reflection of the beam, and let's say the wellness of the process. Some real-time monitoring, as also Rainer shown, we have something similar at AIMEN, but it works with certain structures. When you have some structure that are not that periodic, you have some problems when you want to analyze that structures. So it's an issue that should be solved, but for what we see, it's still not solved. It's something that it's working on issue. So regarding the use of different motion systems, we at AIMEN, inside the NewSkin project, we have built up 5-axis laser processing machine, which is based in the use of a femtosecond pulse laser from amplitude. We have a laser fiber from Photonic tools, stability beam launcher system, which allows you to enhance the point stability at the entrance of the fiber. So we have maximum of the entrance of the laser inside the core of the fiber. So we have a very good transmission of the power from the laser to the other end of the laser fiber. And at the other end of the laser fiber, we have installed a laser scanner. So in this way, we can scan with different angles the surface of the sample. As for example, you can see here in this scheme, we can move the angle that reaches the surface of the substrate by moving the rotary axis that is placed on top of the linear z axis. This allows us to work on different 3D shapes with complex geometries just by analyzing the geometry, how the geometry is, and by planning the movement of the laser, of the 3 axes, and the laser opening and shutting to improve the final pattern. As an example, we have here a small picture of something that we have already printed on a small cylinder. We have being able to print this the logo of the NewSkin project and our own logo with this setup, which is something, it's a basic at starting point, but it's something that by improving the let's say the procedure in the future, is something that we think that we could apply on larger surfaces. But as I said before, if you want to go larger, you will have to go to robots. So the control and the way do you handle the robot and the positioning needs to be improved. Another thing that we are working on right now, also within the frame of this project, the NewSkin project that was originated in a previous project, the Phenomenon project, we started to use diffractive optical elements to shape our array, our initial beam laser, into an array of different, say, array of different beams, parallelizing this beam, or not only using an array of light, but we can tailor the intensity of this array with the DOE. So by changing the shape of the wavefront, you can improve the throughput of the process or produce structures with a higher, with a better performance. This is using DOEs, which are, let's say, a static way of shaping light. If you want to do it dynamically, you want to go to the use of SLMs. SLMs, as you can see in these images, allow you to transfer the image that you have on your SLM into the screen. I mean, you can shape your light into any shape that you want to do and you want to use for the fabrication of different structures. The nice thing about the SLMs is that you can use them in 2 configurations. You can use direct imaging. I mean, you put an image to the screen and use the reflection and as the base image to transfer it then to the surface. you can use you can transfer a face map to the screen, and then use the Świerad optics to produce the same image on the sample surface. We have several setups at AIMEN that we are using for these processes, for them being parallel beam processes, the two processing units. For the use of the DOEs, we just need to put the DOE in front of the object lens, and then we can transfer the design of the DOE directly onto the substrate of the surface of the the surface of the sample that we want to texturize. With respect to the SLM, we need to project that light using a different kind of optics, 4F, in order to project the face map into the through the objective lens on the substrate surface. We have used this to do some tests on glass, and we have been able to fabricate some gratings on glass with by changing the shape of the beam that we were using with the SLM. Okay, summarizing, I mean, this is not so only, it's probably most presentation that raise questions and ask for help in some areas that solve some questions. We have seen that for the texturization of large areas, you will need to go to robots, but it's something that's I think a work in progress. In fact, in the following months, there will be a starting project working on this kind of work, actually trying to improve the control and how the robots and interact with the lasers and with the positioners in order to improve let's say the precision of the positioning, and so the precision on the texturing of the equipment. Online monitoring is something that is needs a lot of work there. We need to look for alternatives, probably with some correlation of techniques, direct measurements, use of artificial intelligence, and optimizing the beam guidance and beam shaping. It's something that's going to be seen on the future of machines. This is how we see it, at least. Thank you for your time. I hope I have been clear. Otherwise, I'm here for questions.
Thank you very much, Francisco, for showing us the projects and also the challenges you have for the future. It's time for questions. I have a question myself regarding the use of SLMs, because it's a component I normally see related with lower power lasers.
Yes.
How do you see the performance and the durability of these elements?
Actually, in the last year, there has been a lot of developments from Hamamatsu, from Holloway, to use these kind of machines with higher powers. They are now cooled by water. They can withstand higher powers, probably not the highest power that some application require, but for some application where you don't have a very hard material, you could use this kind of setups. At least for now, they can withstand really high power short pulse lasers.
Thank you. And as I don't see any other question, yeah, please. We have a question from DMC.
Hi, Francisco. Yeah, thanks for the presentation. It was good to see the 5-axis system pictures as well. I wanted to ask, what kind of 3D shapes are you using? Are you marking using that system? What kind of non-uniform shapes are you processing?
For now, we are using the system to mark on cylinders or molds. For example, for molds for the fabrication of O-rings. So for since I have a toroidal symmetry, something like that. At least for the moment, that were the requirements from some companies that led us to the use of this machine.
Understood. Thank you.
Thank you. Yeah, Dariusz, please.
Hi, thank you very much for this presentation. I was wondering, what is your favorite wavelength? And because I saw, well, some of green, some, I guess, is green the most common that you use?
Well, it depends actually on the application, on the material. We for micromachining, we mostly go with IR with 130 nanometers, but we have several applications with 550 nanometers because we were also working on 2-photon polymerization, and that's the wavelength we use for that. And we started using beam shaping for that application. And then when we see that this beam shaping materials and machines could withstand the higher power laser, we try to use them for that application.
Okay, thank you. And my follow-up question, like, do you see any trend for the future going lower wavelengths?
Well, that's a very good question. Regarding the SLMs, I mean, because when you go deeper, you have higher absorption, so it's complex to manage the energy in that area. So I don't know. Probably if the materials keep evolving, probably they will be useful. But right now, I have seen that they have built something for 343, I mean, third harmonic of erbium fiber laser, but not I mean, not for higher power. I have seen high power for just for infrared and maybe green.
Okay, thank you.
So thank you again, Francisco. And well, to finish the session, as we have been talking a lot about beam shaping, we have a final slide from asphericon that is going to tell us a little bit more about their solutions for that. So Sebastian.
Yeah, Antonio, thank you. All right, yeah, so it's going to be just a quick one. If it lets me, just a second. You can see my screen, right?
Yeah.
Okay, perfect. Yeah, so as stated in the beginning, so asphericon company.
We saw now a duplicated, sorry, Sebastian, we saw a duplicated, so perhaps you need to change the time of a slide or going back and we said without presentation mode. I think that's better.
That's better, yeah. Let's do it like this. Okay, yeah, regarding beam shapers, as already introduced by Antonio, I would like to present some nice results we have achieved together with an institute here in Jena, Otto Schott Institute for Material Research, while examining different focus intensity distributions such as top hat or donut. So this research included mainly 2 points. First is the suitability for material processing with femtosecond lasers. And second, the generation of laser-induced periodic surface structures on stainless steel. So how was it done? In order to generate different focus beam profiles, top hat, donut, or beam waist in different working planes, we used our as we call it, airy shape. You can see it here on the left-hand side. Yeah, what does it do? It basically converts a collimated Gaussian beam into a collimated airy-shaped intensity profile. And then second, we are using a focusing lens to perform Fourier transformation on the input intensity function. And as a result, the corresponding counterpart occurs in its focal plane. So this can be seen also here on the bottom left side. So this is how the setup basically looks like, and some of the results are shown here in the middle, as well as on the right-hand side. And what's the conclusion of all this, and how can beam shapers contribute to a more efficient process? For material processing, it obviously is the enlargement of the channel width and smaller ablation depth due to a more homogeneous distribution of pulse energy over a larger area. And second, and this is what you can see on the right-hand side, the laser induced structuring. It's, yeah, as we have heard it also today, doubling of the scanning velocity and the reduction of processing time by a factor of 2, or up to a factor of 2 with a constant surface structure quality. Yeah, these were our findings, and this is what I would like to present to you today, in addition to all the nice applications and challenges we have seen today. If you need further information, just visit our website or visit our YouTube channel, Shape It Till You Make It, which gives really nice insights into beam shaping and yeah, beam expansion. Thank you.
Thank you, Sebastian. So really nice compliment to all the comments and challenges we saw today. I don't know if there is any question for Sebastian. So my doubt is what's next in terms of pin shaping, because you present today the ARRI. Do you have any other shapes or features in mind for future developments?
Yeah, so as a consequence, so the ARRI shape, which I have just presented, what we have recently introduced beginning of this year was a so-called, as we call it, squarey shape. So it's a rectangular design. So we turn it from a circle into a square. So this has been recently introduced. And yeah, apart from that, if you're playing around in the lab, you'll find a lot of nice shapes and energy distribution, let's say, models. So it's quite interesting. But in the end, yeah, it's simply the demands we see from the market. So anything you can think of, just challenge us, and we try to make it happen for you.
Great, thank you very much. So if there is no questions, I can proceed with the final slide, the summary of our session today. So let me share my screen again. So we have been talking about different things. So first we heard from Andreas the trends in glass manufacturing. So we saw what are they doing in terms of glass cutting. I really like the 3D form glass for these glasses, and also the free forms. Also curious about the thick solutions. And thank you for mentioning this emerging laser dicing of microcomponents using your expertise in the glass. From the discussion, I took that it's good to have higher power lasers with good beam profile and tunable beam shape to get better results in the future. Then we have some presentations about functional surfaces. It was very interesting to learn about DLIP as the proposed technique for getting surface structures in glass. I also like the presentation from Brian with the high power femtosecond laser for scale texturing in the metal coils with a roll-to-roll proposed for mass production. And then from the discussion, also the use of higher power lasers could mean a challenge on synchronization, and then getting better performance in the lenses to not have problems with the thermal effects. And then the quality control proposed is scatterometry as a solution that they think it could be nice in the future. Then with AIMEN, we were talking about this texture on large pieces. So we saw their approach to get these systems with rotary axis to get better performance in texturing and to avoid the problems they have with robotics solutions. And then we talk about online monitoring necessary, and also how optimizing bead guiding and bead shaping to get better results. And as a final point, even if he was not the final one, but Dariusz make a summary of optimized parameters, gave us Fluence for metals and for the electricals to get maximum ablation. I liked also his approach for the intrabar separation of 50 nanoseconds in the case of ablation of copper. And from the discussion about different wavelengths, I get the conclusion that the better results are obtained for these 130 nanometers in the infrared regime. So thank you everybody for being here. It was a pleasure. I think we can stop now the recording because it's almost 5 p.m. the last time, and then we can continue the internal discussion. If there is any other question that you didn't want to address because it was private and you want to do it public, we are now in a small room, so it's nice for discussion. I remember that Antonio has one question missing from Dariusz, no, from Rainer, if I'm right.
Yes, yes.
So that could be the starting point for this conversation.
Yes, so now we are no longer public. We are like at the bar, at the pub. So it's 5 o'clock.